Welcome everyone to one of our very prestigious distinguished lectures here in the Allen School. Today I'm absolutely delighted that we have Sarita Adve visiting us from the University of Illinois at Urbana-Champaign. Sarita has an absolutely encyclopedic list of accomplishments. I just wanted to highlight a few to give you a sense for the treat you are all in for today. Sarita works sort of at the interface of hardware and software, which basically means that's sort of all of computer science, right? There's sort of these two sides, but a lot of greatest hits in programming languages, compilers, operating systems, and of course, architecture and design. And not just great academic successes, also tremendous impact in tools that we all use every day. So if you've ever programmed in Java or C++, you've been, writing code against memory models that Sarita helped design. Again, a list of awards as long as my arm, Ken Kennedy Award, Anita Borg, Woman of Vision Award. We're going to see a great vision today, I think, for the future of research. And also tremendous impact in diversity and mentoring. So nearly every ACM SIG these days has a CARES program. You might have seen this. This helps support graduate students, potentially going through difficult times or trying to figure out how to navigate research careers. Sarita started sort of that whole movement. So tremendous impact. Also, I'm very lucky to be in the Ada Center with Sarita, and that's given me the opportunity to interact with a lot of her students. And I think sort of the best reflection of an academic researcher is what their students say about them, and Sarita students never stop praising her advising and mentorship and friendship. So absolutely delighted. I think we're in for a real treat. And so with that, I'll sort of hand it over to Sarita to hear about vision for the future of architecture, systems, and programming languages research.
Wow, thank you, Zach. Thanks for that introduction. I did want to correct you that something like CARES does not happen with one person, and so this was a group effort with several of us as part of SIGArch. So the title of my talk is Systems 2030: The Extended Reality Case. This is work that I've done with many collaborators who I'm going to acknowledge on the slides. Okay, so I think in this group, we all know that the end of Moore's law and Dennard scaling is here, and this is leading us to the era of specialization. On the left here is a recent iPhone die photo showing how many accelerators, specialized units, this chip has. This graph here on the right was compiled by my colleagues at Harvard, David Brooks and Guoyuan Wei's group. They counted the number of accelerators, the number of separate IP units that each of the recent iPhones had, and you can see that there is an explosion of accelerators on these systems on chips. And so the architecture community has embraced this, right? There's a realization this is what needs to be done. We need specialization, we need accelerators, and there's a lot of work on how you design specialized accelerators. But what I want to talk about today and what we've been focused on is how do you design specialized systems? And by that, I mean not just the accelerators, but how are these accelerators going to communicate with each other? These accelerators are going to need to be programmable, as I'll talk about later. So how do we build the software stack on top of them? How do we write applications for them? And so on. Now, along with all of this, there is another parallel trend of applications. So there's an explosion of applications on the edge. So for example, this one here shows our VR lab on our campus, virtual reality lab. Here we have robots that my colleague Girish Chaudhary has. He has a startup here that builds these robots that go in the fields to do all sorts of things like phenotyping and weed control, etc. This cartoon here represents a project that I'm involved with. IBM is leading it with collaborators at Columbia, Harvard, and others at Illinois, where we are looking at building a system of connected autonomous vehicles that can communicate with each other for better autonomy. So all of these systems have challenging performance demands, very stringent resource constraints, and have end-to-end quality metrics. that we need to abide by. So putting these two trends together, I believe that this demands what I call scalable and generalizable specialization techniques. By scalable, I mean that your end-to-end quality should scale with resource usage. And the more, as you add application features to your application, the hardware and software design time should be proportionately increased, right? So we need scalability on these dimensions. By generalizable, I mean that even though these techniques need to be designed for a specific application, they need to generalize across systems. So they should be application driven, end-to-end quality driven, and lead to hardware software application co-design systems. And so by that, this is what I mean by, or what I believe the systems of 2030 will need, technologies that can help us do all of this. Okay, so all that is very great. And we want to do research like this. We want to build systems for 2030, but what application do we start with, right? So this work is application driven. What application should we use? And this became a real stumbling block for us. So we were doing a lot of work in accelerator communication interfaces, compilers, and whatnot, trying to attack heterogeneity in systems. But we were frustrated by just the toy benchmarks and the toy applications that we had to work with. And so we decided, well, we're going to take a detour and try and come up with a realistic application testbed that will enable us to do better and more grounded research. And so we hit on, or we chose to use the extended reality application for our work. So why extended reality? Right, we think that this is really a spectacular goldmine case for the kind of research we want to do. Now, by extended reality, or XR, I include virtual, augmented, mixed, etc. reality. And many people believe that XR is going to be the new computing interface. It is going to be pervasive, certainly going to affect science, medicine, entertainment, education, and our lives. XR is challenging in the sense that there is an orders of magnitude power, performance, and quality gap between what we can do today and our ideal aspirations. It's very diverse. So this domain involves graphics, vision, audio, video, robotics, optics, haptics. And so the idea is that if we can build technologies that can help us design good XR systems, they will apply to other subdomains as well. And it requires full stack optimization. So there are challenges that span hardware, compiler, OS, and algorithm. And finally, there are many end-to-end quality of experience metrics that the system has to maintain, and these are all user-driven, human perception-driven. So there's a lot of flexibility and a rich space of trade-offs that a system designer like me can have fun playing with. So this is a great driver for research for Systems 2030. And so we set out to build and research XR systems. And before I go ahead, this is a slightly complicated looking table, but just to get grounded in reality, we put together through a literature search requirements for XR systems that the consensus that was evolving for requirements for XR systems. So you don't need to look at the whole table. What it's showing is for a state-of-the-art VR system here, the HTC Vive Pro. What is it giving us? What does it have on various metrics that we care about? And what is the ideal? So this ideal is, it's a consensus that is emerging. People don't agree on exact numbers, but there is a consensus. And then on this side, we have AR. So there's HoloLens 2 as a state of the art, and then there's the ideal. And again, we don't need to go through all of the rows, but just to highlight a few. So when it comes to resolutions or megapixels for VR, you can see for both VR and AR, there's orders of magnitude gap. When it comes to power, the VR system is actually running on a server. It's not tetherless like we would like it to be. It's not mobile. So in fact, there's just a huge difference in the power, right? So the server takes hundreds of watts, and we want 1 to 2 watts if you really want a headset to be sitting on our heads and so that we can walk around. And then for AR, HoloLens 2 takes about more than 7 watts, and the ideal requirement is 0.1 to 0.2, because AR glasses, you expect that you're going to be walking around with them all day, and so you don't want the thermals to burn your forehead. Right, and so, and it's the same story on many of these rows. So it's an orders of magnitude gap in power, performance, area, weight, and quality of experience metrics.
So one quick question, Sarita. So this seems like a great challenge problem because it spans so many different areas of computer science. One thing that I'm curious about, I mean, is it really everything? Is there anything that we can use unmodified? Like, what's the starting point? I guess I see a few numbers here where we're already pretty close or even within the ideal range. So like, are there technologies that this grand challenge doesn't need to revolutionize, or is it really sort of ground up rethinking of everything?
So the way to think about it is, so you might say, okay, motion to photon latency, which I'll describe later, is, it seems like it's on track, right? But the way to think about it is that if you don't have this motion to photon latency, which really is about the time taken from the user's head movement to the display, right? Give the image that the user is supposed to see right now, right? So if the motion to photon latency was too high, the user would vomit, right? And so you can't sell systems like that. Okay, so what you do then is you trade off other things, right? You trade off, you have lower megapixels, you have lower field of view, etc. So there's this rich space of trade-off, right? So obviously systems exist today, right? People are using these systems, okay? But they're making all these trade-offs to, so like, this VR device runs on a server. You can't put it on your head and walk around, right? And so what is the starting point? I mean, the beauty of this space is there are starting points that we can use and do better and scale up.
And I guess the big challenge is not just all these requirements, it's all of them at the same time.
Precisely. That is the point that I'm going to make over and over. Okay. Yeah. All right. So yeah, you don't want to work in an area where there's no hope whatsoever, right? You want to see incremental progress, and so this has that quality as well. Okay, so challenges for XR systems research. Now, the good thing is that XR touches so many domains, but if you want to do research in this area, this is a bad thing because it needs expertise from so many domains. So where, we set out to build this benchmark suite, this test bed. Where do we start? Okay, so there's so many things we had to deal with. But the bigger one was that XR, the interfaces are closed. Now, recently, there's been a major development where there's been a standard called OpenXR that has opened up the application runtime interface. But within a runtime, within a XR device, what's happening, it's all closed and very closely guarded by industry. There are no open source benchmarks or systems that give us guidance as to what is being used by industry. So this was a big problem. And what I'm going to show you is that we've been able to address this no open source benchmarks or systems. And that's what Elixir is, the topic of my talk is about. So Elixir stands for Illinois Extended Reality Testbed. It is the first open source full system XR testbed. It has state-of-the-art XR components integrated with a modular and extensible runtime. It is OpenXR compatible. It provides several quality of experience metrics. It runs on desktops and embedded systems. And soon we're going to launch a community consortium with several industry and academic partners who've helped us along the way and encouraged us to do this work. But we're going to launch an official consortium. ARM, Facebook, Micron have been our very early supporters. NVIDIA has joined. And so the idea is to have a community resource that people can contribute to, and also be able to standardize benchmarking on these platforms, which are fairly complex, and standardize quality of experience metrics so that we can do research and move this space forward. So I believe this is provides a rich playground for Systems 2030 as well as XR research. So just to show that this is real, right? This is not just vaporware. So this is a demo of a subset of our system. So what you see down here is my student walking around in our lab in the physical world where he's navigating through this virtual world on the left here. So this left side shows a third it's a third-party kind of a view of the world, the headset's view, as this headset is moving around, or rather, it's a third-party view of the headset moving around. The right side is what Elixir is delivering. So this is the left and right eye buffers that Elixir is delivering, and as you can see, as the headset moves, as my student moves, Elixir does a pretty good job. I don't know what Zoom is doing on your screens, but on my screen, it's doing a pretty good job tracking and rendering and displaying these simple scenes. Okay, so this is great, right? So what is the problem? Well, the problem is that in this case, in this demo, Elixir is running on a pretty beefy desktop. If we ran Elixir on an embedded system, and I'll show you the results of that later, the experience is not so good. Okay, so Elixir is real. You can get it from elixir.github.io, and I invite you to play with it. So let me briefly pause here to give a shout out to Team Elixir. We have several students, all of them amazing. Elixir would not have happened without many external consultations with, again, people from academia and industry, and I want to acknowledge several of the people who were particularly helpful to us. And while all of my students have been fantastic and contributed to big pieces, I have to highlight Josefa, who is who leads this project, and the project started due to his passion, continues due to his passion, and he's just amazing. And I also want to highlight another student, Sam Grayson, who joined much later than Josefa, but in his very first year, he built the runtime or led the building of the runtime, which is a fairly complex project. Okay, so what does Elixir look like, right? So digging down a little bit deeper. So there's 3 different pipelines, interconnected pipelines. This is a generic XR workflow. Most XR systems have this. So there's a perception pipeline, a visual pipeline, and an audio pipeline. And these, each of these consists of several components, and they are connected by the Elixir communication interface and runtime. And all of this runs on a hardware platform, ideally a mobile device, but we run it on desktops and embedded devices. And we can run XR applications. Today we can run OpenXR compliant applications. We have a leverage. We were lucky that the Monado group has built an OpenXR interface, and so we were able to leverage that for our work. Okay, so I'm going to give you a quick overview of what these individual things are, not getting into too much detail, but just to get an idea. So the perception pipeline. This consists of sensors like cameras and inertial measurement units. A key component of this is visual inertial odometry. It's a form of SLAM, for those of you who know about SLAM. It's responsible for providing the position and orientation of the user's head or pulse, and this is a really critical component. The IMU, which is takes the readings from the sensor, integrates them, and provides high-frequency pose estimates because VIO, the visual inertial odometry, is slow, and so we need to give the system intermediate pose estimates. The pose predictor does some extrapolations for the future. We have scene reconstruction, which builds a dense 3D map of the world. We have eye tracking, although this is not completely integrated because there are some issues with sensors not being available. Okay, and then we have the visual pipeline.
So from that previous slide, I take it that Elixir focuses on the inside out
Yes,
kind of tracking rather than
Exactly.
the outside in?
Exactly. Yeah. So we're moving around and with cameras, exactly. Yeah. So the visual pipeline is the key part of the visual pipeline is what's known as asynchronous reprojection, commonly known as time warp, and there's also space warp, which we are in the process of integrating. The idea is that the application gets the pose from the perception pipeline, and it renders the frame for that pose, but in that much time, the user has moved already. And so when the application submits the frame to be displayed, the system checks the user's pose again and changes the perspective of the frame slightly so that the new position of the user can be reflected. And this is a really it's a simple computation, but it's a very critical computation. This is responsible for cutting the motion to photon latency that I was alluding to earlier, because it's taking advantage of not just the latest pose, but it also does a prediction of where the user will be looking when this particular frame is actually displayed. So there's a lot of communication going on with that time warp is doing with different parts of the system. Then there's lens distortion and chromatic aberration correction, which is essentially correcting for some optical issues due to curved lenses, etc. In the future, we're going to see adaptive displays. This is an interesting thing that is caused, addresses a problem that's caused because of human anatomy related issues. Our eyes, there's something called Vergence accommodation conflict that can cause fatigue and headache if it's not taken care of. In general, our eyes, the focal plane, the current displays have just a single fixed focal point, but our eyes can converge at different points, and so this discrepancy can result in really bad fatigue. And so there are displays now with multiple focal planes that can address this, and this is done through something called computational holography that we support in Elixir. And finally, the audio pipeline, which delivers 3D spatial audio. We have audio encoding, which encodes multiple sound sources into something called higher order ambisonic sound field, and then a playback, which rotates and zooms this HOA sound field to reflect sound at that is correlated with the user's latest pose, so the user can spatially correlate the sound. And this also performs another stage called binauralization to account for the user's ear, head, and nose. This is very specific to the user's shape of the user's head, and this we do this as well. So all this to say that Elixir includes state-of-the-art components, state-of-the-art algorithms, and it's a fairly complex system. But really, XR is not just a collection of components. It is a system. What do I mean by that? So it's no use to us if you just, well, it is useful, but what we want is not just these individual components. We want to know what the system is doing with these. So for example, the IMU is running at a very high frame rate. Camera runs at a slightly slower frame rate. They both communicate with the VIO, which takes the information from them. The IMU integrator takes information from the IMU and the VIO. Eye tracking does its thing. Scene reconstruction communicates with camera. Scene reconstruction, IMU, eye tracking communicates with the application. The application renders its frames, gives it to reprojection, which takes the new pose, and hologram does communicates with reprojection, and audio encoding does its thing, and audio playback gets the pose from the IMU, and so on and so forth. So there's a lot of things going on in the system, right? We have different components working at different frequencies, multiple interacting pipelines, and there's synchronous and asynchronous dependencies, and there are multiple quality of experience metrics. So the image quality is one metric, motion to photon is another metric, audio has its own metric, and the runtime, the system has to take care of all of this. So at the heart of all of this is a runtime that is orchestrating all of these dependencies and all of these components. Okay, so the Elixir runtime is we've put a lot of thought into this because this is really the heart of the system. And what we have is what we believe a very modular and flexible architecture. So the Elixir components are essentially plugins for this runtime. They can be separately compiled, dynamically loaded, which means that we can easily swap and add new components, configure the system with a subset of components, add in new implementations, because a lot of these components have, they're evolving as we speak. So, every few months it's a new algorithm, and we want to be able to swap that in with the older algorithm. So we've taken pains to ensure that researchers can have this possibility. And then the runtime also has to keep track of all of these dependencies, right? So, and the data flow and the communication between these components. So we have a very efficient, flexible communication interface when a component is configured in the system, it specifies event streams that it publishes and subscribes to. We can have synchronous or asynchronous consumers. We have a copy-free shared memory implementation, which makes this very efficient. When I will show you our numbers, you will see that the runtime really hardly has any overhead. In fact, it doesn't even appear on our graphs because it's so efficient. So we have an end-to-end system that balances flexibility with efficiency. It's an efficient system and yet a very usable research test bed. Okay, as far as applications, we can write XR applications directly to Elixir, but more, it's what's more exciting to us is with OpenXR now, there is a whole universe of OpenXR applications exploding, and the Monada group has done an awesome job of building this OpenXR interface that we are able to leverage. And so today we can run the Godot game engine, which is an open source game engine with many applications. But soon, hopefully, Unity and Unreal, we run Linux, so that's been one issue, that Unity and Unreal don't have OpenXR versions for Linux. But soon, hopefully, they will have those, and then we'll be able to run those game engines as well. Elixir also provides end-to-end quality metrics. I mean, that's the whole. That's a very important part of this work. So we measure motion to photon latency. Again, this is very critical. It's time from the user's head motion to the display of that perspective. We have metrics for image quality. This is, as I will describe in a bit, these metrics are also a big part of, these are really moving targets and research topics by themselves. We have state-of-the-art metrics for today, and I will show you why they're not nearly as good as we want them to be. But we have the state-of-the-art, and we are flexible. We can add more as things appear. We measure pose error and relative pose error, and we have extensive telemetry, the usual frame rates, misframes, time distributions, power, etc. So this is the set of components that Elixir supports in detail, but pretty much everything that I talked about, and in some cases multiple versions, multiple implementations. So we support several this is actually out of date. We support many more cameras and IMUs, different VIO implementations, different scene reconstruction implementations, etc. And they're written in a variety of there's C++ and CUDA and OpenGL and so on. Okay. So this is the full system, right? But each of these components has many different configurations. Okay, so the camera, for example, runs at different frame rates, right? It can run from anywhere from 15 to 100 Hertz with different resolutions, different exposure. The IMU has a very large range of frame rate. The display has all sorts of different configurations in terms of frame rate, resolution, field of view, and same thing with audio. So one of the first painful part of running experiments with Elixir was tuning the system. And there are no automated ways of tuning something like this today. So what we did was just simply hand tuning, looking at, visually looking at the quality of experience that we had, and tune the system so that we got a good quality of experience on our desktop. Okay, so these parameters listed here are the final tuned parameters. And it turns out that a lot of what we're doing, every time Facebook or other companies release information about how they tune the system, it's an extra validation that what we're doing is right. And as I said before, we've talked to and had the system vetted by many companies and many researchers, and it's been as validated as such a system can be. Okay, so
sorry, Sarita, one quick question. So these are sort of per component tunings? Like if a new camera comes out, do I need to retune the whole system with that new camera in it, or can I do experiments with that camera, or Or what's the
Yeah.
additional effort when new components are released?
Yeah, so this is a research thing, right? So this is one of the research problems that I'm going to talk about. I won't get time to talk about the research we are doing with Elixir, right? So I have like one slide for each project, but I doubt I will get there, okay? But how do you tune automatically a system like this is a key problem that we are studying, okay? And today, again, I can do a per component tuning, right? I could do that, right? But the question is, will I get the best out of my system by doing that, right? Versus an entire end-to-end retuning, right? And we've seen over and over again that the entire end-to-end retuning, and not the whole system, right? So for the camera, when you're looking at VIO, for example, the exposure of the camera made a huge difference because it changed how much time was available and so on for things downstream and so on and so forth, right? So yeah, research problem, okay. But we are confident that the configurations that we are providing are solid configurations. And you remember that community consortium I talked about? Part of that is to come up with standard sort of configurations, benchmark scenarios, so people can do research in this area and we can compare apples to apples, right? Okay. So yeah, so so that was about tuning the system. The platforms that we run on are, we run on a high-end desktop machine. Again, this is not what we desire, right? Because the power is crazy, but this gives us an upper bound. Okay, today this is a high-end machine, and how well does it do? And then we run on embedded NVIDIA Jetson platform with we run it in two different modes. One is a high performance mode and one is a low power mode, and this is closer now to the types of systems that that we would expect this workload to be running on. And for applications, we use the Godot game engine, and on top of that we run several applications with various levels of graphics intensity, Sponza and Materials Platformer, and this is an AR demo that we sort of built, customize ourselves to get some AR experience. Okay, so just to show the results, right? What can we get out of Elixir, and what is the implication for architects and system designers? Okay, that's the goal of that's what we're trying to get from these results. All right, so there's lots of stuff here. I'll walk you through this really quickly. This is the frame rate. Okay, so each of these columns is one particular component of or one particular sub set of Elixir. So this is the perception portions of the perception pipeline that run at the camera frame rate. So the camera and VIO run at the camera frame rate. So since this is a graph for frame rate. Then we have the IMU part of the perception pipeline. This is the visual pipeline, which runs at the display frame rate. And this is the audio pipeline, which runs at whatever is appropriate for audio. And each of these axes, the top here number is the target frame rate. Remember when I talked about tuning, we set the frame rate. So this is where we want to be. Okay. The rows are the different systems. So this is desktop, this is the Jetson HP, and this is the Jetson LP. And each of these graphs for a given component, like the camera here, has 4 bars, and each of these bars is a different application. Okay, so what's going on here? All right, so let's just look at the desktop, and we can see for the desktop everything pretty much meets its frame rate, right? So everything is hitting the top. There's a few drops for this application, but it does more or less all right. Okay, so the desktop does great, but the problem, of course, is that the power is totally off the charts for us, right? So the 200 watts. The Jetson LP, things start to fall apart, and visually we can see that the experience is pretty bad, right? So the only thing that Jetson LP can run at the target frame rate is the audio up here. Okay, but this is where we want to be in terms of power. Actually, we want to be much less than this, but this is closer to where we want to be in terms of power. And the point to take away is that this gap is going to only increase as displays and components scale. So this particular configuration, for example, doesn't have scene reconstruction, and the display is not, the megapixel is not where you want it to be. Okay, this graph here is time per frame, and this is really the opposite, right? The flip of frames per second. And the reason I'm showing you this is just to see, so the organization is the same as before. The red lines here represent the deadline that each of these components needs to hit. Okay, so if you're above the deadline, means red line means you're not meeting the deadline. And the numbers on top, which you don't need to read because I'm going to show you a graph, but these numbers represent the standard deviation of the time. Okay, so here is that standard deviation seen more pictorially. Okay, so you're going on the x-axis is time flowing, and on the y-axis is the amount of time that these different components take. And I have two different graphs because if I show this set of components up here, the axes are very different, so we won't be able to see much. And so again, you can see as before that the Jetson misses deadlines, a lot. The desktop mostly meets its deadlines, but the interesting thing is the variability that we see. Now, VIO and application, which is at the top here, these are input dependent, so we expect variability, although not this much. So there is, so there's variability. But all of these other components here, these are actually not input dependent. And so if you run each of these components by themselves in isolation, you will see flat lines because there's no input variability. So what's happening here is that the input dependence, the scheduling, and resource contention is leading to significant variability, which is then, of course, affecting the quality of experience. And of course, you can see where this is going as far as systems research goes. And the next thing is the distribution of cycles. So, you can ask, well, is there one component here that's really responsible for all of this, or is everything responsible, right? Where do I focus? So this graph here shows the desktop, the Jetson HP, and so this is the desktop, the Jetson HP, and the Jetson LP, and it shows the distribution of cycles. Okay, so for each of these, which component took how much time. And we can see, like, normal architecture systems design approaches, application and VIO dominate here, the blue stuff and the orange stuff. Let's accelerate those, get them going, and we're done, right? That's what you would say. But the problem with this approach is that reprojection, which is this small little thing here, okay, and the IMU integrator, okay, which is this thing here. These are small, they take little time, but when it comes to the quality of experience, these are really important. These are what affect the motion to photon latency, the pose quality, etc. So we can't just think about the application and VIO dominating and fix those and be done. We need to consider all metrics, and in this system, if you look at all metrics, it turns out all the components are important and need to be considered together. Okay, power. All right, so power again, we have the desktop, the desktop, the Jetson and the Jetson LP, and you can see, as expected, the desktop is like, nice hundreds of watts. Jetson LP is lower, but this graph here on the right is more interesting. What this shows is the distribution of where power is being dissipated. Okay, so let's focus on the Jetson configurations. Architects usually look at CPU, GPU, and memory power, which is the lower part here. And indeed, about 50% or so or more in this case is being used in those subsystems. But the rest of this is SoC power or system power. So this includes things like microcontrollers and so on that happen on the SoC, as well as system power, the communication to the sensors, and to the display, etc. All right. So again, the point is that we need to consider the entire system, going back to the beginning. So system level components such as display and I/O that are really, really important. Going to quality of experience. So this is motion to photon latency. And again, we see desktop. So if you remember, we talked about 20 milliseconds for VR, and the desktop is just fine. But the Jetson starts to level off, starts to get bad. And for AR, we want about 5 milliseconds motion to photon, and it's nowhere near there. But what is important is that the variability is really high. And so we can see this in this time display that even though in some places the Jetson HP on average seems to meet the motion to photon latency, but there's so much variability, which and we see that when we see the visual experience, it's not very good. And again, showing that this end-to-end motion to photon latency and looking at it from a systems point of view is really important. Okay, so we get an extremely unpleasant experience on the Jetson. So motion to photon is one quality metric, and then there's also image quality. And I was mentioning earlier that we have two different metrics here, SSIM and FLIP, which is a very recent metric by NVIDIA researchers. And here, again, it's not surprising that we see that the Jetson number is lower, right? We sort of expected that. But there is something else that is surprising. So these two right columns are the errors in the pose. So this is in terms of degree, okay, how, the head rotation of the user, how well you predicted it. And this is in terms of meters. And you see here that this is saying that the system is off in Jetson LP by 138 degrees. So, the user's looking this way and the system saying the user's looking 138 degrees away. So of course, I mean, this is not represent, what you're going to see on the screen is not going to be representative of what you expect to see. So it's crazy, right? But what is interesting is when we saw the frame rate for Jetson LP, the VIO and camera frame rates showed that we were meeting these frame rates, on average pretty well, right? But clearly something's off, okay? Another interesting thing is that this SSIM, which is supposed to reflect image quality, says it's 0.68, which is not 1, which is supposed to be the best case, but it's not like 0 either. I mean, this should really be close to 0. So something, what's going on? So there's two issues here. One is, connecting this, the pose error with the frame rate. We see again an argument for considering end-to-end QoE. Right, so architects tend to look at, okay, my VIO is running at appropriate frame rate. Yeah, I dropped a few frames here and there, but look, this drop, these few frames that were dropped, really resulted in, completely losing tracking, and that was, had a huge impact. And the second is we need better QoE metrics. The SSIM and FLIP are really not doing justice to the fact that this is a really bad image, and this is. These metrics were not really defined for XR. They come from other contexts to measure image quality. They don't have a sense of the temporal perspective, etc., that XR needs. And so this is research in progress. But what Elixir gives now is an end-to-end system where researchers can do research to develop new metrics or validate new metrics. Okay. So I've shown you a lot of numbers, right? I want to put together all of the implications that I sort of hinted at all through. So, what does this really mean for architects and system designers, right? So, I've talked about all the things here, but the power performance QoE gap, we knew it existed, but this is the first empirical quantification of it, at least an open quantification of it, and clearly shows we need to specialize the hardware, software, and the system to get to where we want to be. No application component dominates all metrics, which means we must consider all application components in the system together. We need to think about the entire system. Power consumption goes beyond CPU, GPU, DDR, means we, again, need to consider system-level hardware components. Variability means we need to partition, allocate, and schedule system resources. And the QoE related observations again show we need to look at the entire system to make QoE driven trade-offs. All of these things are things that I talked about in the context of System 2030. And Elixir provides us with a testbed that can open up doors for doing research in these areas. So I talked a lot about this system, but we also want to dig deeper into each component and see, I mean, are these components interesting, or what's going on there, right, in the individual components? And so here is microarchitectural information about all of the components that we have in Elixir, showing the black line is the IPC, the instructions per cycle, and the different parts of these graphs show the cycle breakdown in terms of microarchitectural utilization. And you can see that there's a lot of microarchitectural diversity in these components. So it's not just that, if I fix the front end, I'm done, or if I fix the back end, I'm done. No, it's like everything. There's a lot of diversity. Okay, so wide range in IPC and hardware utilization. And then we also looked at each component and dug deeper into the subtasks of these components. Okay, and looked at it in great detail. So VIO has all of these different subtasks, how much time is being spent in them, what is their detailed characteristics, etc. And what we found is, just in these components, there's like 27 different tasks and no task dominates. Okay, and then we went in and we looked at computation patterns and memory patterns, and we saw again lots of diversity. So there's integer stencil, and there's histograms, and there's QRD composition and ransack in terms of computation patterns. And for memory patterns, there's locality in some patterns, and there's global sparsity and completely random accesses. So again, very, very diverse. So we did this for all of the components. Don't need to go through them. So again, even weighing down a bit, looking at individual components, we find there's an abundance of tasks and no single task dominates, which means we need automated techniques to determine what to accelerate. This is not a case where we spend remember the design time scalability, right? So this is not a case where we spend hours and days and years of time looking at individual tasks. I mean, there's just too much going on here. And it's, we believe it's impractical to build an accelerator for every task in any case. There's leakage issues, there's area issues, there's, how are they going to communicate with each other issues. So we believe we need to build shared hardware. And how do you do that for such a complex system? How do you design such a system? The diversity of primitives means we want a flexible on-chip memory hierarchy, a flexible accelerator communication interface. And all of these algorithms are in flux. So as you saw, we're already supporting multiple algorithms. So we believe we need to design programmable hardware. And these different algorithms have different QoE versus resource usage profiles. So we believe there is a need for end-to-end QoE-driven approximate or opportunities for approximate computing. So again, in other words, Elixir provides a rich playground for Systems 2030 research, and I invite you all to use it. So I had a few slides on how we are exactly using Elixir in our research. I don't have the time to go through them, but I did prepare slides in case there are questions. So we are using Elixir for our research on an accelerator communication interface. We have an IR, a compiler IR, that we believe is the right way to represent heterogeneous parallelism in software. So we've been working on this for a while, called HPBM. But Elixir gives us, a real workload, a real system to test this out. So we are working on representing Elixir in HPBM and using this for code generation for accelerators, for automated accelerator selection, approximations, and resource mapping. We have work on so this work, the previous work is with Vikram Adve and Sasha Misailovic. This work is also with them. It's about automated approximation selection. We have a lot of work going on here in the past, but now bringing it to this rich space of Elixir. We're working with folks at Harvard and with Vikram, David Brooks, Vijay Reddy, and Guyan Wei to do automated selection and generation of accelerators, hardware and software. We're looking at QoE-driven scheduling with Brighton Godfrey and Radhika Mittal at Illinois. We're looking at how to expand Elixir to deal with offloading of computation, content streaming, multi-party experiences with Ada Gabrielowska, Georgia Tech, and Clara Narsted. So again, and there are more use cases. I know Francie is looking at security and privacy with Elixir, and several others, other researchers are starting to look at various aspects here. So, besides the research, we're also, as I said, continuously developing the testbed. We really want this to be a resource for the community. Lots of stuff still to be done, and we are about to launch a consortium so that the community can have a say in this work. So just to wrap up, I started off with challenging with various applications that all have challenging performance demands, stringent resource constraints, end-to-end quality metrics. And I hope I convinced you that these applications require new ways of doing systems research, and Elixir provides a rich playground for research for Systems 2030. And although we started with XR and Elixir was designed for XR, we are finding that all of the technologies that we are developing through Elixir are actually applicable to these other domains as well. So we've started to apply our work to the Epochs project, and we're using it for the EarthSense robots and so on. So we believe that Elixir is a rich playground for Systems 2030 and opens up doors for scalable and generalizable specialization, for application-driven, end-to-end quality-driven hardware-software application co-design systems. So I will stop here. If people and take questions, and I had a couple. Oh, I do want to give a shout out to my team again, plus the Spandex team and HPVM team, which really got us going in this direction. And then I have a couple of slides about some sort of stepping back and perspectives on life and lessons for a couple of minutes, but I will take questions.
Let's just do questions really quickly, and then I'd really love to see those slides, Sarita, if you can stick around. So I see Dan immediately had his hand up, so go ahead and call on Dan first.
And I'm going to ask my question and then probably run. It's that time of day here. For fantastic talk, really thought-provoking, and your implications for architects in particular was like, well, we need this and we need that and we need all these things. I mean, I was sitting here thinking, well, is there anything we can get rid of? And like the only thing I could think of is maybe you don't need hypervisor support. Do you have additional ideas on things that you might be able to simplify in this domain?
Simplify is the watchword, Dan. This is, at that power, it's all about simplifying, right? So specializing, is all about simplifying. And the trick is, how do you do that while meeting all of these constraints? So just to give an example, the Spandex work that I didn't get to talk about, this accelerator communication interface, it's all about CPUs have done coherence in this complicated way forever, right? And now we have accelerators that are starting to do some coherence in very, very simple ways, okay? But it doesn't quite work. And this is a whole talk. So what Spandex does is provides an interface so that we can have specializable coherence that is simple, just the right primitives for just the work you want to do. Okay, so it sounds kind of cliched and hackneyed, right? I agree, but that's really the goal. So simple is what this is all about.
And I'll go ahead and step in for Dan. I think he's had some parenting responsibilities to jump into. But maybe a follow-up to this is, when you set up the goals, we both want scalable performance, but we also want scalable development. And that's it's sort of immediate tension, right? Because when I think about getting performance, I think about breaking abstractions. When I think about accelerating development, I think about having more abstractions. And so I think what was really surprising is the abstractions you have for these components in their interaction is so cheap. So is that coming from spandex having sort of the right primitive, the right notion of consistency, or how am I able to sort of have both the performance and the modularity to reason about my application?
Yeah, so there's no spandex in Elixir today, right? The test bed out there is like, that's not on. So we are taping out spandex on a chip in the Epox project, but today there is no spandex in Elixir. Okay, the abstractions, again, the Elixir abstractions, we just spent a lot of time thinking about them, right? But that's sort of the runtime abstractions. I do want to talk about abstractions and interfaces in general, right? So this is like a pet thing for me. It's what I think about when I think about designing systems. And spandex is an abstraction for accelerated communication, but HPVM, for example, is an abstraction for the hardware. Okay, it's a virtual ISA, it's a compiler IR, right? It's what the role that LLVM plays in sequential computation. We think of HPVM as playing that role, and so this abstraction it includes parallelism as a first-class citizen. It includes heterogeneity, and it includes data communication within the IR explicitly. And so what that is allowing us to do, again, this is work in progress, what that is allowing us to do is to use this one common HPVM representation to compile to a variety of accelerators, not just compile to them, but also use it to do automated analysis for accelerator selection and generation and hardware software co-design, code generation, etc. So Zach, I think this is a very rich area. I'm not saying these are the right answers, but there's hope.
Yeah. I have a ton more questions. I also want to make sure that we also make space for others. So one that we had in the chat, but I missed during the talk was, how does the nose affect sound? Now that was from about 34 minutes ago, so I'm not entirely sure which slide nose and sound go together on. Does that question make sense?
I actually had a picture, but I wasn't sure of the copyright, so I removed it from here. So it's actually the shape of your head, okay, affects how you localize sound. And so this is 3D spatial sound, right? And so how there are some transfer functions that you apply to the sound field so that it reflects the shape of your head, your nose, your ears, etc. And we use these are not user specific HRTFs, which is the transfer function. There's a lot of research in the audio world to actually get user-specific HRTFs so that you get, user-specific localization of sound. So yeah, it's a very deep connection.
Yeah, I'm always surprised at how hard audio ends up being. Like, BBN of networking fame, I think started by doing like speaker configuration or something, and it just sort of it blows up in complexity.
It's really fun. I mean, this whole domain has been so much fun.
Okay, I'm getting some comments in direct messages and chat with votes for the bonus lessons. So
okay, this had better be worth the hype, right? Let's see.
I have every confidence.
Okay, so I didn't spend as much time on these as I should have. But here are some life stories and lessons, right, from this work and some other work I've done. So the Elixir story, so I alluded how it was born out of frustration, right? That we were working with these toy benchmarks, and we were doing all of this work on compilers for heterogeneous systems, accelerated communication, and so on and so forth. And this was just this desire to impact something real. And I laugh now when I think about it, but I had absolutely no clue about XR when we started this, right? And the only thing I had going was that my colleague Steve Laval, he had recently returned from Oculus after a successful stint as founding chief scientist. So I figured I'd learn everything by osmosis or something. So we went, Josefa, my student, and I went to Steve one day and said, how do we design hardware for this? And Steve, I didn't understand a word of that conversation, honestly. But Steve was very encouraging and very happy and excited. And if you know Steve, you should get to know Steve. He's just always like that. And then CFAR, which is the center that DARPA SRC sponsored center, which is a precursor of ADA that Zach mentioned. They had this seed proposal call. And so I wrote this one page. It really had nothing of substance in it. All it said was, I'm going to do a VR benchmark, and Steve Laval is going to help me. And it was a small amount of money. Steve was encouraging, and I had this hyper excited student, which really made all the difference. And so that's how we started Elixir, which was supposed to be a detour, right? Now I laugh about it. I thought it was going to be like a few months of cobbling together some benchmarks. And this just became my main research thrust for many years. And now, many students, faculty, and industry collaborators, I mean, there's just a lot going on. But I have to say that it's been 3+ years of work, really hard work. The real impact is still to come for this one. This is still not there yet, but it's already very satisfying. Okay. So this and the next slide I'm going to talk about sort of distilling lessons. So this is the story for Elixir. And then I was thinking about my career. There's another big piece of work I did, which is the memory models work, and that story is sort of like this. I was doing hardware memory models. I did that for my PhD thesis for 10 years, trying to get people to understand what this was about. Couldn't make a difference. Very frustrated. And then my students and we wrote a paper that was a retrospective of hardware memory models, calling on the software community to fix things, because my approach for the hardware memory models was to take a software-centric view. And I guess I didn't have any credibility in the software world. Nobody listened to me. So unless the software people did anything about it, this was not going to fly. So we wrote this little thing saying the software people should fix it. Bill Pugh happened to read that. He was thinking about the Java memory model and how it seemed buggy. He asked me to join the effort, and I did. I'd never programmed Java before. I didn't know PLEs. I don't think I ever did a PL course. Somehow I graduated, got a PhD in computer science without doing that. I had no students doing this, no funding. And it turned out to be 5 years worth of work, one paper, but real impact. Okay, and again, I'm going to relate this back on the next slide. The third big piece of work that sort of comes to mind, it was a different form of work, and that's the story. While I was chair of SIGARCH that Zach alluded to. As you all know, diversity in our field is not the greatest, and several of us were frustrated. But some colleagues gathered data on this in the architecture community, and that really increased our frustration. And so one thing led to another, and several of us joined hands for some really intensive activism, but leading to concrete actions. There were many things that we did, we're very proud of. Made a lot of enemies on the way, unfortunately, right? Because this requires.
I feel bad for them.
For this. What?
I feel bad for them. I feel like anybody who's like not on Sarita's good side is in trouble. So yeah, I think.
Well, anyway, it was like nearly 3 years of work, no papers, right? But real impact. And Zach talked about the CARES movement. And it received the CRA Distinguished Award recently, so very satisfying. So what are the lessons, right? For me, this is what works for me, right? Follow your passion, okay? Do things you really believe in and you want to do, right? Take risks, okay? Everything, all those 3 things that I said are literally Elixir. The first year we talked to people, we wanted to do this. They were all very friendly, but most of them looked at us like we were crazy, because it's like, how are you? This is all closed. Industry guards this. Nobody's going to tell you anything. You're never going to get anything done. Okay. And same thing with the diversity stuff, and the memory models was very similar. The memory models work took like 20 years to actually get into people's hands. So you have to be passionate to do that. Take risks, believe in yourself. And this is something that I really want to drive home. Impact, strive for impact. And for me, what it means to make an impact is changing people's minds. And this takes time, it takes hard work. This is not the same as number of papers. Okay, sometimes it is, sometimes there's a correlation, but sometimes it isn't. And finally, there is nothing that I've done by myself, right? It takes a village. A lot of people have to come together, and they do it, and they help me in many ways. And I strongly believe in paying it forward, and I hope you will do too. These are people who have inspired me, and I always like to acknowledge them. Janie Irwin, who's sort of symbolizes the paying it forward culture. Mark Hill, very similar. And then my family, of course. And then there's the whole thing called work-life balance, which is a whole other talk. But yeah.
I think I'm getting a message here. I think we're probably going to go ahead and wrap it up.
Yep.
Sarita, I hope that, the pandemic and lockdown ends soon. I would love to have you actually come so folks can see you. For anybody who, if you somehow missed it during the talk, Sarita sort of projects enthusiasm in person in a way that's incredibly contagious. So we'd love to have you in person so we can all, get charged up with some of that vibe. We should definitely do it in the winter, right? Sort of bringing the sunshine into UW. I think it'd be great.
Okay.
but thank you so much for the wonderful talk. And hopefully we'll see you in person soon. For everyone out there in TV land, thanks for tuning in. And make sure to stay tuned for future talks from the Allen School.